in heaven, give us this day our daily bread, and forgive us our trespasses. We forgive those who trespass against us. Lead us not into temptation, but deliver us from evil. So tell us, Lord, mercy and us. In Jesus' name. Julia, Daniel, the other Daniel,
Here.
Olivia,
Here.
Samantha, Julian, Claire, Allison, Lauren, Granville, the other Samantha, Brienne, Nicole, Cassandra, Annika, Christina, Decus, Alexandria, Annabelle, Ryan, Ariana, Leah. So today, what I want to do is establish that the majority of the questions in 4-5 are things you guys are comfortable with. So what I'm going to do is I'm going to start by picking one or two that you may or may not have attempted and checked your answers for. And then, at least for a while anyway, ask if there are any that you had trouble with, rather than me just picking them. I anticipate that before the end of the period, or near the end of the period, we will have gone through enough of a variety of these, using the steps that I articulated in the insert, so that there shouldn't really be any more issues with the stoichiometry. You guys gonna keep doing your math, or are you gonna do the chem? Is that chem?
This can.
Do you have a question with one of the things we did?
I'm a little bit
Which
like
question?
This is question 2 on 213.
Question 2 on 213?
Yeah, the practice problem.
Well, maybe let's start with question 2 on 213. Well, why not? Consider the unbalanced equation, that one?
Yes.
Did you balance it?
Yes.
Okay. So when you balanced it, 2 in front of ammonia and 2 in front of water,
Yes.
and 2 in front of sodium hydroxide, right?
Yes.
Okay. So let's load that one up. So where do your 2 molehills go?
Underneath this one here, and then underneath.
So underneath ammonium sulfate?
Yes.
And underneath ammonia,
Yes.
correct? Okay. So when this equation is balanced, there's a 2 there, a 2 there, and a 2 there, yes?
Yes.
Okay. How many liters of ammonia measured at STP? Molehile goes here. Are formed by combining a solution containing 40.5 grams of ammonium sulfate with an excess of sodium hydroxide. Anytime you see that, it means don't worry about that compound. So there's where the 2 molehills go. Let's read it a second time. How many liters of ammonia? That's where you're gonna end up at STP. And you're given an amount of this.
I know you're right.
So grams, because it's not the solvent that reacts, it's the solute. So grams ammonium sulfate to moles. Moles there in a 2-to-1 ratio. However many moles of ammonia you have, that's 22.4 liters per mole. And then you want your final answer to be 366. 322.4 and also 3 there. And did you get it? Did you check your answer?
No, not yet.
Check your answer, because if you did it that way, very unlikely you're gonna get it wrong. As long as you got the right molar mass, and as long as you got the balanced equation,
Thank you.
okay? Did any of you try number 3 and experience problems with it? Is the conventional wisdom out there overall that you're trying these and you're getting them right? That's good. That's the way it should be. How about we go this one? I don't think we did this one yet, did we, in class? Number 3 on page 215. This is the last practice problem in this section. Notice how many things you gotta know how to do here. She doesn't give you the balanced equation. She doesn't really give you the product. She gives you a clue though about product when she says carbon dioxide. You have to know what the formula for phosphoric acid is. You have to know what happens when you react an acid with a carbonate salt. Remember, that's that third category of double replacement where we form water, carbon dioxide, and a salt. But because it's a form of double replacement, the suggestion I made when we did that, treat it as double replacement. The product, one of the products is unstable, it's carbonic acid, but build carbonic acid, balance carbonic acid, then whatever coefficient you have in front of that, convert to the same number of water and CO2. So let's balance the equation. Phosphoric acid, acids come from 8 anions. So it's obviously a solution because you're given a molar concentration. The solvent's water, reacted with excess potassium carbonate solution. Even if you pour phosphoric acid on solid potassium carbonate, you're going to get the same reaction. Okay, but she's put it in solution. Let's just exchange the ions and balance it that way. This cation's going with that anion, so that'll give us potassium phosphate. As we've mentioned before, but I probably wouldn't expect you to remember, potassium plus anything is soluble. And the other product is the hydrogen from the acid goes with the carbonate, and carbonate salt, and we get this. But we're not going to put a state there because it doesn't stay that way. So it looks like phosphate and carbonate are balanced, but let's start with potassium. We've got 3 here and 2 here. Least common multiple of 3 and 2 is 6. So let's put a 3 there and a 2 there. 2 phosphate, 6 hydrogens, 6 hydrogens, 3 carbonate, 3 carbonate, so we're done. Now we can do the stoichiometry. So let's read the question. How many liters of carbon dioxide gas would be formed? Well, we look at this and we go, we don't have carbon dioxide. But then we remember, this is one of those double replacement reactions where that, being an unstable acid, immediately decomposes into the same number of water and carbon dioxide. So that plus that. And now you can put states in, right? So the question begins with, how many liters of carbon dioxide gas? Which means a molehill goes here. Would be formed at STP if that volume of that concentration of this solution were reacted with excess potassium carbonate. So the quantity of the phosphoric acid that was given, and that isn't a quantity, that's a concentration. That's the quantity. So we need a molehill there. So now we know which 2 species are involved in the chemical reaction. We have the balanced equation. Now let's read it one more time. We want to end here. Liters, and you don't have to write STP, but I'm putting that in just to remind you to think 22.4 liters per mole. And to answer that, we're given a quantity of the phosphoric acid. But in that case, we're given volume, not of the gas, but liters of the solution. So there's no requirement here for a periodic table. There's no molar mass. This is volume of a solution in which there is a solute that reacts, which produces ammonia gas, which we can calculate the number of moles. So that's where we want to end. That's where we start. So step one goes from volume of solution to moles of solute. And even if we don't know how we're going to do it, that's what we have to do. Being at the top of that molehill, we can now go all the way over here to moles of carbon dioxide. Once we have that, we go to liters at STP. Now, those little pyramids and the arrows are just to get the calculation sequence. That's all it's for. So we start with liters of phosphoric acid solution. And remember, it's the solute that reacts. So that's why we're doing moles of this. This is dissolved in the solution. So liters of the solution is converted to moles of hydrogen phosphate. That's what reacts. That's step one. Step two, that's balanced equation. So moles of CO2. And step three, liters of CO2 and STP. All we did is write those arrows out horizontally. Now we take care of the units. If that has to cancel, it has to go here, liters of solution. That has to go down here for the same reason. And that has to go down here. All I'm doing is following the steps in that insert. Now I've articulated them in the insert as 8 steps. I don't care how many you call to label them. After doing 2 or 3 of those, it doesn't even matter what step you're on. All you're doing is following the logic. Get rid of these, replace them with these. And just a reminder, don't leave just the arrows there. An arrow isn't a mathematical symbol for an operation. That's just the order. Change the arrows to multiplication signs. So what do we start with? We start with 1.5 liters. This capital M means moles per liter, okay? So you have to know what that means. And that's the same units that are in here. Don't do this. That makes no sense. If you put a capital M there, that's wrong. That means moles per liter squared. What's a liter squared? So this does not mean moles. And that's why you're going to that unit here. It's up to you to know that that capital M really means moles per liter. And if you know that, then right away you have the number, 1.75. That's how we get from here to here, concentration. This is balanced equation. In this balanced equation, 3 moles of these things are produced for every 2 moles of those consumed. So in other words, that equals that in terms of this reaction. And the letters STP tell us that 22.4 liters of any gas contains ammonia. Make sure the units work. They should, based on how we set it up. The only unit we don't have a line through is that. And notice we got 3 sig figs here, 3 there, but only 2 here. So our answer can only have 2. And those aren't considered measurements, those are exact numbers counted. So it should be the 2 sig figs, liters of CO2 and STP. Now if you set it up that way and you're reasonably proficient with your calculator, you can't get it wrong. It's very difficult to screw this up. But check your answer anyway. And again, I've said this tons of times. Let's say you do this at home that way. You check your answer, it's right. Then one of the reasons you do your homework has just been achieved. You convince yourself you know what you're doing. Don't do 6 of them and then check your answers. Because if all 6 are wrong, then 5 of those were a complete waste of time. If you do it this way and you check your answer and it's not right, and you don't know why it's not right, or let's say you get to a particular step, you can't get any further, ask me. And if that's the case, then your homework has also done its job. It's convinced yourself you don't really know what you're doing. Those are the only two reasons to do homework. I'll give marks for homework now and then, but that's not why I give it. I don't give it for marks. It's so that you guys realize if you understand what you're doing or not. And let's say you do a bunch of these and you keep getting them right. Then imagine what that's gonna do for your confidence going into the next test. It's gonna remove a whole bunch of stress that would have otherwise been there. The worst thing you can do is not do any of them. Because then you have no idea that you don't know what you're doing until you get your test. And that's a nightmare scenario, because now everything you're doing is gonna cost you marks. So homework is for your benefit. I don't always give time in class to do stuff, but because this is that important, that's why I do. Now, let's have a look at some review questions. Are there any that you attempted and they gave you a particular headache with? Yep.
On page 218, question 13,
Okay.
what's a reducing agent?
That's a good question, and it's an unfair expectation from Sherry. I'll tell you what it is, but I wouldn't put that on a test. So what type of reaction is this? Zinc replacement. So what is the zinc doing? Is it giving away electrons or gaining them? It goes from an atom to a plus 2 ion, right?
Yeah.
So it's losing electrons.
Yeah.
That's what a reducing agent is. A reducing agent means the agent of something else being reduced. In other words, that thing is causing something else to gain electrons. So a reducing agent is the thing that loses electrons. But we haven't done section 4.3, so that's unfair. So just to save time, let's grams of zinc, okay? The reducing agent is the thing that's oxidized. It's the thing that gives electrons away. It's the reason that tin gets reduced. In other words, tin has to get the electrons from somewhere. It gets them from the zinc, all right? But I couldn't put that in, that'd be unfair. But she's given it to you, assuming in section 4.5 you did 4.3, right? Now, once you have that, that's not too tricky, right?
Mhm.
Any others that you did try and gave you some trouble? Okay, well, let me pick one or two. Okay? Number 20 is very similar to that, very similar. We're asked for a volume of a gas at STP formed from a volume of a solution. So the steps are virtually identical to this. Volume of solution, to moles of solute, to moles of gas, to liters of gas at STP. How about we try this one? This one's not really difficult, except the wording is something you might want to think about. The acetic acid in a 2.5 mole per liter sample of a solution of kettle-stale removal. What is that? It's usually just an acidic compound that dissolves calcium carbonate. But you don't need to worry about that. The acetic acid in a 2.5 mole per liter sample of a solution is reacted with, that makes it a lot easier, is reacted with an excess of lead-2 nitrate solution to form a precipitate, which is then filtered and dry. So what type of reaction does this look like as you read it?
Double replacement.
Double replacement. You're not reacting the acid with the base, so it's not neutralization, but it is double replacement. Now, I wouldn't expect you to know necessarily what the precipitate is. But one of the products is gonna be a nitrate compound, right? Nitrate's always soluble, so that ain't it. So the precipitate would be the lead compound. So knowing that, if you haven't done this one yet, try it. Try it out. And remember, ic acids come from 8 ions, so acetic acid is the acetate anion plus hydrogen. And write it like this, okay? That's acetic acid. And that's the hydrogen that it loses, okay? And to the extent you're able, pretend you're doing this at home, or even better, pretend you're doing it on a test. You'll have your table of ions, you'll have your periodic table. You're gonna get an activity series. If I expect you to actually determine states, if I don't make it real clear in the question, then I give you the solubility table. But right now, I'm leaning against that because it's not gonna affect your ability to do stoichiometry, it just might be something else you have to worry about. See if you can follow the steps closely. Generate the balanced equation, read the question a second time, where the molehills go. Read it a third time, what units are you given, what unit you want to end up with. Then draw the arrows, write the horizontal sequence, put the units in, put the numbers in, do the math. there's a chemical species, let's just balance it. We got 2 nitrate here, 2 there, 2 hydrogen. That hydrogen is that hydrogen, okay? So 2 acetate, 2 acetate, 0. So you recognize an acid either by starting with an H except for water or ending with COOH. So ic acids come from 8 ions, so that is the acetate anion, and that's the hydrogen ion. And if you want to do that a little differently, that's the hydrogen, which is here, okay? So when you see acetate in your table of ions, it's written CH3COO minus. And acids release hydrogen ions in water, that's the hydrogen. So when we take that off, we're left with the acetate anion, okay? That's how acetate's written in your table, agreed? Okay. And the reason we write the 2 O's separately is because they're not connected together. So acetate is that. And that's why we don't write that hydrogen there. We don't write CH4COO, because this is the hydrogen that makes it an acid, okay? These things aren't what we call acidic hydrogen. So that's why we write it there. And the oxygens aren't stuck together. They're next to each other, but we don't write CO2, okay? Anyway, all we have to do is read the question another time. What volume of the solution was required to make that mass of precipitate? Well, we're told that we have an excess of the lead 2 nitrate solution, meaning that's not part of the chemical calculation. We need it to do the calculation because we have to balance the equation. But this is the solution for which we are given a quantity. We're given that concentration. We want to know what volume of that solution it will take to make a particular mass of this precipitate. So that's where our 2 moles is. We want volume of this solution, so that's where we want to end. And we're told we make a mass of that precipitate. So that's where we start. So rather than asking how much of this can I make, we're saying this is how much I did make. How much of this must I have made? Okay? Now, does it mean you gotta read this thing a couple times maybe to get that? It might, but that's not a bad thing. Oftentimes you read it once, make sure you got the balanced equation. Read it a second time, where the molecules go. Read it a third time, what quantity am I given? What quantity do I need to have? And remember, a concentration isn't a quantity, it's a ratio. So, we start with this mass. That has to be step 1. In other words, how many moles of lead 2 acetate do we make? Balanced equation gets us the moles hydrogen acetate, which is the solute in acetic acid, and that's only available in the solution. So it's a 3-step problem. Write out the units. Grams of lead 2 acetate. Moles. Again, just as per our diagram. Moles lead 2 acetate, 2 moles acetic acid. And because that's in a solution, that's our last step, liters of that solution, okay? Grams of lead 2 acetate has to go here, and you know know how to do that, that's periodic humor, that's molar mass. Moles of lead 2 acetate have to go here, and anytime you have moles on the top and moles on the bottom, it's coefficient for balanced equation, that's step 2, okay? According to this equation, it's gonna be a 2-to-1 ratio. So moles of lead 2 acetate goes here. And moles of acetic acid goes here. So again, that's molar mass, you guys can do that. What does she give you for decimals? So there's 3 sig figs here, there's only 2 there. So your answer can't have any more than 2. So if we make 8.64 grams of precipitate, let's see. 15, 27, 32, 53. 53 times 206, 207.2, 206, 313.2, give or take. What's the mole mass? What is this? Do what you guys check your answer.
0.021 liters.
Say again?
0.021 liters.
What's the mole mass on that 2 acetate? That's what I'm
Oh,
asking.
that's 325.47 moles. Sorry, grams.
Maybe.
200.
Might be wrong.
There are 266. There's 3 carbons.
Okay.
Oh, I didn't double it. Oh, I'm fucking stupid.
2-to-1. And this is the inverse of concentration. Notice it's not 2.5 liters per mole. It's 2.5 moles per liter. So make sure the numbers that go next to the appropriate units. So grams cancels. And again, we want our answer. Or if you want liters of acetic acid solution, we want our answer to 2 sig figs. Remember, these are not measurements, they're exactly as you count.
I'm actually so tired.
Now, once you've written it out like that, whether you determine it on your own or doing it from the board, then check your answer, see if your calculation gets you the right answer to 2 sig figs. Okay? Now, there's not a lot of room underneath each question, but there might be sufficient room to write this. Now, do I need to see this on a test? No, but it might be in your best interest to put it in your book, so that when you're studying from it, you can see exactly where these things came from. And that's not only gonna be important for the test for this chapter, and that test is not gonna be a long way away, but you're gonna see stoichiometry again in the final exam. And I'd like to think that this makes sense to you now, but 4 months from now or 5 months from now, if you don't have something clearly written in your book, you're gonna go back on it and it's gonna be a dim and distant memory. In other words, if this is all you write and you don't write this, how did you get that? You might not remember. But if that's under this, it'll be crystal clear, even 5 months from now. Or even when you get to first year university, where stoichiometry is gonna be a thing. There's a big chunk of grade 11 that professors expect you to be fluent with in first year. Stoichiometry is one of them. So don't throw your book away. I will try one more that I will pick, but are there any that you guys have trouble with? Yeah.
On page 217, question 4.
Okay, let's try question That one?
Yeah.
Oops, not that one. That one?
Yes.
Okay, I don't really like how Sherry's worded this, because after all she's gone through to explain what the word mole means in a thermochemical or delta H notation, she didn't even put it in. So this is what she should have added. It's in a balanced equation, correct? So because of that, this means when that happens, when that amount reacts with that amount to produce that amount, that's the energy required. Does that help?
Yeah.
So if we look at the question, we don't need a molehill here, because we're converting an amount of a chemical to energy. So let's, without drawing any molehills, let's see if we could at least calculate what our conversion sequence has to be. How much energy will be required to complete the reaction of 12.2 grams of sodium to produce sodium oxide? Well, we're given grams of sodium, and we want to end up with kilojoules, right? Now, because that unit should be moles, and notice in this equation, that means when 4 moles of sodium are burned, right? So, but we have that conversion. So we're gonna go grams sodium to moles sodium, and that's easy, that's periodic table. And once we know how many moles of sodium we're burning, we can go to kilojoules. So let's just let the units take care of themselves. Grams go here. Moles goes there. So we start with 12.2 grams of sodium. And if we're gonna go to 2 decimal places, according to the periodic table, it's 22.99, I believe. If we stopped here, we'd have moles sodium. But in this balanced equation, we're not burning 1 mole of sodium, we're burning 4. So the 124.7 is for 4 moles of sodium. You see why that is?
Yeah.
And then your answer should have 3 something. I don't know what it is, but that should be how you do it. So I think she made an error here. She left out something she shouldn't have left out, okay? Can you see why in number 5 she gave you the balanced equation? That would be kind of tricky to balance, wouldn't it? 3 reactants, 4 products. Did you check your answer? Is it right?
Yeah.
Let's see what else. Any others? Yep, sure.
Could you please re-explain which elements can and can't replace each other in a single?
Look on page 175. That's the list. Now, you don't have to memorize that. You would get it. But metals replace metals,
Yeah.
non-metals replace non-metals. So on the left side of that table, any metal above another will replace it. So for example, if you look at lithium, it'll replace anything on that list.
Okay.
And what it's replacing is a metal cation in a compound. So the lithium will become the element, the ion will become, the lithium will become an ion, the ion will become the element, okay?
Okay.
The hydrogen there in all caps, and Sherry puts a little asterisk there, any metal above hydrogen will replace hydrogen from an acid, but the metals above magnesium will replace hydrogen from water. And I would give you that little explanatory thing in the bottom with it. The only thing you use that for is for single replacement reactions. You don't use it for anything else. But it'll tell you if it will proceed or if it won't, okay? Let's see. Why don't you try number 20? That's the last question. And then we'll at least start 4-6. Now, if what you're doing in your book, if the only writing in there is the ones I'm doing for you on the board, then that's kind of not the point. So if that's what mostly your book looks like, at some point over the weekend, try a variety of questions. Try a mass to mass, try a mass to volume, try a volume to mass, try a volume to volume. Look at different variations on the theme, and each time you do one, check your answer. And if there are any issues at all, let me know at the beginning of class on Monday. And then check your answer. And if you get it right, then you don't need to go through on the board. Remember, hydroic acids are binary, just like hydrochloric is HCl, hydroiodic is HI. And this is, in terms of your calculation sequence, identical to number 3 on page 215. You're calculating the volume of a gas at STP. You begin with the volume of a solution whose concentration you know. Notice that in number 20, although 22.4 liters per mole is 3 sig figs and 0.185 moles per liter is 3 sig figs, 150 milliliters is 2 sig figs. So your answer should only have 2. You don't really need to know that the zinc iodide is soluble, but you do need to know that hydrogen gas is diatomic. There's the balanced equation. And if you check your activity series, zinc is indeed above hydrogen. It'll replace hydrogen from acid but not from water. So, what volume of hydrogen gas measured in STP, we need a mole here. Is formed at STP by the reaction of excess zinc metal, which means that's not part of the calculation, with that volume of that solution. So, we need a mole here. The only thing that goes on a mole hill are quantities. So we want to end with that quantity. At STP. It's not really likely to be at STP because the test tube's gonna get hot, but for calculation purposes, it's fine. And we start with liters of this solution. And I'm just gonna convert 150 to liters, okay? So we start with this, step 1, step 2, step 3, just like number 3 on page 215. So we start with liters of hydroiodic acid solution. According to this, step 1 is to moles of the solute, which is what reacts. Step 2 is to moles of H2. And step 3 is to liters of H2 at STP. Liters of solution goes here. Moles HI goes here. Moles hydrogen goes there. So what volume of solution do we start with? 0.15 liters. And that's 2 sig figs. I'm not writing 0.150. This is concentration. In every liter of solution, you have 0.185 moles of HI. This is balanced equation, as it always is. So in this equation, 1 mole of hydrogen gas equals 2 moles of hydrogen iodide. This is 22.4. And notice that this mole conversion has 1 in front of the mole. This mole conversion is 1 in front of the volume. Okay? Liters of solution cancel, moles HI, moles H2. You want your answer to 2 sig figs. That would be liters of H2 gas at STP. Okay? That's very straightforward. So, try a variety of the questions. Yes?
For the balanced equation, does
Yep.
it matter if we have zinc first or the
No,
hydride?
doesn't matter at all. Doesn't matter at all. But notice that neither of these are metals, but because hydrogen is a positive ion, that's what zinc is replacing, right?
Yeah.
But no, I don't care what comes on the left or the right, doesn't matter. Any questions? Okay. So, ones that I haven't done, and ones that you either haven't, or maybe tried and didn't get correct, try that variety between now and Monday. And if we start Monday with the majority of you being clear on this stuff, which is to say you did and you keep getting the right answers, then the purpose behind all these review questions has been served. That you, in other words, you've convinced yourself you know what you're doing, okay? And it's actually nice to learn that you know what you're doing, and then you think, how could this get any more fun? And then you turn the page and it does. I like the way Sherry's worded this section, because real world stoichiometry. We've been making some simplifying, easing assumptions up till now, but now we're gonna talk about more real world chemistry. One of the things we're gonna talk about is excess limiting amounts. So in other words, up till now, even with the question we just did, this amount of this is reacted with excess of this. We were always told what we had too much of, which meant what we had too much of is not part of the calculation. But what if we're not told that? What if we're told we got this much of this reactant, this much of this reactant, how much of this can I make? Well, you gotta find out what you're gonna run out of. You gotta find which one's the chocolate syrup, if you will. Okay, we'll talk about that. The other thing we haven't included is the fact that no chemical can be 100% pure. There's always impurities in it. Now, sometimes the impurities are in what we call trace amounts, so they're not significant. But sometimes the purity of what you're dealing with means the mass that you're measuring is not all that compound. Something else, some of that mass is something else. So if you use all of that mass to predict products, you're always gonna over-predict the amount of product you can make, because some of that thing you started with wasn't that compound. We're gonna take care of that. Percentage yield, sometimes because of this, sometimes because of reaction conditions, sometimes because some reactions, when the products start being made, they turn back into reactants. Very often, the yield that we predict with stoichiometry is less than the yield we actually get. And that comes under the heading of percentage yield. This is gonna take a little while. But when you look at the warm-up, you think, well, she might have called Gary, there's an ice cream sundae, what's that got to do with it? It's actually kind of simple, almost brilliant on Sherry's part. Let's say you have reached the pinnacle of your career aspiration and have decided as an adult you don't want anything better in your life than to work at Baskin Robbins. So you're making ice cream, okay? Suppose you're working at an ice cream shop. Hopefully it's just a summer job. A group of customers come in and they would like to order ice cream sundaes. Because you're limited in your mental capacity, you need the computer to tell you how to do that. But let's say it's there, and you've got to follow the recipe. So according to that computer direction to make an ice cream sundae, you need 1 scoop of vanilla, 50 milliliters of chocolate syrup, and a cherry. And the computer inventory page says you have 6 scoops of ice cream in your inventory, which can't be a very big store. You got 200 milliliters of chocolate syrup, and you got 475 cherries. So Sherry says, how many sundaes can you make? Can you make 6? Can you make 475? How many can you make? 4. That's limiting reactants. Let's say that's the product. These are the reactants. As soon as you run out of chocolate syrup, you can't make any more sundaes, right? So in other words, the amount of chocolate syrup that you have limits the amount of sundaes you can make. It dictates the amount of sundaes you can make. But it also tells you how much of these things you're gonna get left over. So if you can make 4 sundaes, you've got 2 scoops of ice cream left, and you got 471 cherries, right? Now, chemistry's not quite that simple, but that's the idea. The question is, when you're looking at amounts, let's say you got this volume of this solution, and you got this mass of this reactant, which one are you gonna run out of? It's not as easy as this, but once you know which one you're gonna run out of, then it is that easy. And Sherry's method for determining which one you're gonna run out of, to me, is a little bit too much work. And that's why I've added a second insert into this. Let's look what she tells us here underneath. So far, I don't know why it keeps jumping around like that. This is supposed to be a touch screen. So far, we've made several assumptions about the chemical reactions we've been studying. Given a balanced chemical equation and the quantity of one of the reactants, we've assumed the reactant provided is completely pure. It never is. If I order chemicals from a chemical supply company, or let's say I work at Pfizer, or let's say I work at Fisher Chemical or any pharmaceutical company. Obviously, the chemicals that I use to make the pharmaceuticals have to be really pure. And that level of purity is called analytical grade or reagent grade. The impurities are only trace amounts, but they're still there. But if I'm just ordering chemicals so that a reaction will proceed, for example, the lab you guys are going to do at the end of this chapter, I don't need highly pure, and which means highly expensive chemicals. I order what's called technical or lab grade. Because I'm not measuring amounts, I'm just observing what's happening. But if you use that level of impurity to predict products you can make, or let's say I want to make this amount of product, how much of this will I need? If the thing you're calculating isn't pure, then it's not going to make as much as you think it will, because some of that stuff won't be the compound. Nor, when you calculate how much you're going to need, if you calculate how much of the pure stuff you're going to need, that's not going to work when what you're actually using is impure. So we're going to do calculations on that. The reactant will be totally consumed in the reaction as the reaction proceeds entirely to completion. Even if you have excess reactant, that doesn't mean necessarily that the reaction's going to completion. Which is like, how could that be the case? Up till now, we've been assuming that reactants go to products. In other words, that's a one-way error. But I don't know if you guys remember, at the very beginning of this year, I said if you had to pick one word most important in Chem, certainly in the first half it would be mold. But in Chem 12, that word is equilibrium. And it might surprise you to know that many chemical reactions are reversible. Meaning as soon as the product starts to form, it starts turning back into reactants. So the arrow you're going to get used to seeing in grade 12 looks more like that. Which begs the question, why, God, would this want to turn back into this? That's a good question. It has to do with what drives things in nature, whether it's physical changes or chemical. You don't need to know this for this chapter, but there's two driving forces in chemistry and physical changes. One of the things is nature loves low energy. So when I drop this felt pen, it's never going to hit the roof. It's always going to hit the floor because nature likes low energy. Same with chemical reactions. A lot of spontaneous reactions are exothermic. Forests burn down with a match because nature likes low energy. But there's also a whole lot of reactions that are endothermic and happen by themselves. So what's going on there? It's not energy. Well, there's another driving force in chemistry. And you haven't heard of it before. You've heard of enthalpy, potential energy that can be absorbed or released as heat. That's on those potential energy diagrams. But there's another property called entropy, which is disorder or randomness. And nature loves disorder. She prefers disorder. Nature will never choose order by herself. And really, as we're going to see in grade 12, if I teach you next year, it's going to be, if I'm still here, it really is an idea of probability. So let's say you go down to the beach. Is it likely that at any point ever, the tide will build you a sandcastle? God knows. There's countless trillions of ways those sand grains can be arranged on the shore. But there's only one way they can be arranged such that it builds a sandcastle. So nature will never do that for you. Another way of asking, you spend a whole bunch of time and you build a perfect sandcastle where all the sand grains are exactly where they're supposed to be to make that sandcastle look like that. That's the only way those sand grains can be arranged. But there's countless trillions of ways that they can be arranged in other ways. So what's the probability that when the tide comes in, that sandcastle is going to still be there? 0. Because nature will make what happens the most likely thing to happen. Throw up a deck of cards in the air. Are they all going to land in?
Good afternoon, staff and students. As a faith and Learning community, let us prepare ourselves for the end of day prayer. In the name of the Father, the Son, and the Holy Spirit.
And also, a quick reminder, please keep Brother Bassett in your prayers. Dear God, grant each of us a listening heart, so we may lead with wisdom and compassion. Grant each of us an understanding soul, so we may hold our judgment and be willing to forgive. Grant each of us an open mind, so that we may continue to grow in love and service. Amen. St. Thomas More, pray for us. Blessed Edmund Rice, pray for us. Live Jesus in our hearts forever. In the name of the Father,
So,
the Son, and the Holy
Real
Spirit.
quickly,
Amen.
those arrows are going in different directions. It usually means that in one direction, nature gets to low energy. In the other direction, she gets to disorder, which she loves. You don't need to worry about that, Caroline. We'll pick this discussion up about limiting reactants, percentage yield, percent purity, only after we are all satisfied on Monday that there are no remaining issues for 4 o'clock. But you've got to tell me that, because I can't read your mind, oddly enough.